Okay, so when we stopped at the end of the last class, that part I think was not recorded, but anyhow, I was trying to motivate as to why we probably would want a way of evaluating transfer function of any circuit, right, without really writing the KVL and KCL. Because sometimes writing KVL, KCL, while they give all accurate answers, they are sometimes not intuitive, and sometimes, we probably wouldn't even require the entire complexity of the transfer function that we get from KVL and KCL, right? So having said that, so I tried to motivate as to why we, if there is a easier way of figuring out the transfer function, what are the things that that process should have so that it becomes easy, right? So if I have a big transfer function and if I have a big network, where writing KVL and KCL for the big network is, while accurate, is hectic job, and then putting things together, algebraic mistake, all those things can happen. Nevertheless, if I have to develop a framework in which I am able to find out the final transfer function or the coefficients of each of the terms of a, s square, s cube, and so on, then the framework should also not be very complicated, right? That framework can be different, should be different, but we should be able to evaluate those coefficients without really causing too much of algebra, right? So that's the motivation. Okay, so now let me take a toy example. Let's say a classic RC ladder, something like this. Let's keep second order. Right? So again, motivation is not to write the entire KVL, KCL. Now, you can imagine it can be several, I mean, you can have multiple orders, you can have multiple C's, multiple R's, but let's concentrate on this RC ladder to begin with. So in this case, if I have to develop a framework, so I have to understand what is the smallest section that I can evaluate without writing too many equations. And in principle, the smallest section that I can evaluate is probably 1R and 1C, right? And I can, if I extend that thought, I can probably say that if I have only one capacitor and everything else around is a resistor or non-memory element, then that is also probably easy to evaluate, right? So what I'm trying to get at here is, let's say you have a network in which C1 is not there, right? Let's say C1 is 0. So C1 is 0, which means open circuit. And you have C2. So I know readily what the transfer function of the circuit is, right? I do not have to write anything down. Similarly, if I assume C2 is 0, right, then also I know what the transfer function of the circuit will be without breaking any sweat. Correct? Similarly, if I assume C1 to be let's say infinite, right? When I say C1 is infinite, physically what I'm doing? I'm shorting the capacitor. So in that case also, this is easy to evaluate. Correct? Similarly, if C2 is infinite also, it is easy to evaluate. Now, the key thing to note is that why is it easy to evaluate? Is because by setting these capacitances or the memory elements to either 0 or infinity, I am able to take them out of the equation. Right? So I am able to make the circuit, if let's say I am able to develop a framework in which only one capacitor remains and everything else is either open or shorted, then that network is easy to evaluate. Do you agree? So if that is easy to evaluate, then I mean the framework that we are planning to develop, is something that that should use this handle where so that I maybe open some capacitor, short some capacitor, and so on, and then subsequently go ahead and evaluate it. Okay. This framework it's in place for a while. People have been trying to evaluate this, to come up with this framework since 1950s. There has been a lot of improvement on this. The last work that was done in this domain, which kind of sealed it, was in this paper, Generalized Time and Transfer Constant Analysis by Ali Hajimiri. I will provide the link later on. So, I mean, you can go through the paper. It's a tutorial paper. It's very easy to read, very well written. He has a YouTube lecture also on the same thing. So I'm basically, this entire, whatever material I'm going to cover today and probably in the next lecture, will also be motivated or inspired from his work. Okay. Okay. So let's begin. Another disclaimer before we start today: you have to be in your peak attention, because there are a lot of nomenclatures, lot of algebra, which will be related to certain circuit configurations. The algebra initially might seem a bit tedious, because the development of the framework might seem a bit tedious. There will be a lot of superscript, subscript, this and that. So you will lose one. If you lose me somewhere in between, you will not be able to follow what's going on later on. But once everything is done, you'll see that the ultimate framework is very simple. But getting to that framework will require a lot of notational awareness, right? So be present mentally, and also stop me if you have some questions, right? Okay, so let's begin. So let's assume any network which has, let's say, and I will start off with assuming that the network only has capacitors as a memory element. It can as well have an inductor. I'll do it with capacitor, and then later on in next class, we'll say how to go about doing it with inductor. Framework will remain the same, but just handling things is easier if you have one type of memory elements. So let's say I have a network in which this box stuff inside is memoryless. And you have multiple capacitors connected to it. C1, C2, dot, Cn. And maybe you have an input somewhere here in another port, and it drives through. So in general, I can write the transfer function to be A0 plus A1s plus A2s squared plus to all the way up to ans to power n. And the denominator is really 1 plus B1s plus B2s squared plus. Okay, so now let's do the easiest one first. What is A0? How do I figure out what is A0? Right, so I basically, A0 is the only term which does not have any s, right? So if I have to then massage this equation in order to knock off all s, right? Then what should I do? In the circuit, everything that has multiplied by s, anything that gets multiplied by s should be set to 0, right? So which means that in the circuit, if the only memory element is capacitor, I have to set all the capacitors to 0. Correct? So that is an important aspect, which even though it's obvious at this stage, but we'll be using it multiple times. Okay, so A0 is basically the transfer constant maybe my output is somewhere, I don't know. Maybe I have another port where I'm getting the output, right? The transfer constant is basically the relationship between input and output, right? So this is the relationship between Vi and V0. If both the input and the output are voltages, then the ratio is a transfer function, but it need not necessarily be the case. Hence, it's called a transfer constant. Okay, so transfer, the A0 is the transfer constant when all Ci's are set to 0. Correct? Okay. So that is easy to evaluate. Now I will bring in the first level of notation here. I'm basically following whatever Professor Hajimiri has in his paper. Yes.
In the system, means memory-less system, there could be also some C's.
No, if it has a C, it is memory. It has memory. If there is a C, I have taken it out in the ports, right? So whatever, so everything, if there is a C, that is outside. Okay. So now the first notation is, this transfer constant in this case, we'll note it as H superscript 0. Okay. So H is basically because it's a transfer function, that is H. Now this is not to the power 0. This is superscript 0. This essentially means anything on the, for whatever we do in today's lecture, whatever is there in the superscript essentially means that all C's are set to 0. Okay. You will see that there will be a case in which there is a subscript and a superscript. And that definition will be, in that case, the definition will slightly change. I'll come to that when I talk about it. Okay. So now let's concentrate on these terms, right? B1A, B1S, B2S squared, and so on. So if I want to, okay, before I go to if I want to, so can you comment on what will be the form of B1S? Or rather, what will be the form of B1? Can it have only resistance? No, right? B1 cannot be, I cannot have B1 to be only R, right? Because S is there and the sole, I mean, S has appeared because there is a C. So B1 must have a C, right? But can B1 be only C? It can be? Okay, so if it is C, then I mean, what is the unit of B1S? What is the expected unit of B1S? It's dimensionless. B1S is supposed to be dimensionless, right? So B1 has to be 1 over frequency because S is frequency. So should have the unit of time, right? So which means that B1 cannot be only C also. It should be R, some R times some C. Do you agree? Okay, so basically B1 has to be some form of time constants multiplied and all those things, right? So we understand that B1 has to have a unit of some R times some C. Correct? And it not necessarily be, it is like 1 R and 1 C. It can be a summation of multiple R's and multiple C's. Correct? Next question. Can B1 have 2 terms of C? That is, can it have C1, C2? Why not? Then I'll have S squared. Right? So that is reserved for B2. Right? So B1 cannot have 2 C's. So similarly, B1 cannot have 2 R's. Because I cannot have 2 C's, I also cannot have 2 R's. Fine? Okay. So now that much we understand. So let me just then keep it simple and say it's a second order circuit, right? So I will not write up everything till S to the power n. So let's say it's only a second order circuit. So we say that HS is equal to A0 plus A1S plus A2S squared by 1 plus B1S plus B2S squared. So this is only assuming second order circuits. And we understand that B1 will have the form of some Ci times some Ri. What is I? What is Ci? What is Ri? We'll talk about it shortly. Similarly, B2 should be of the form of, now can you tell me? So in this case, I can say that B2 will have the form of some CI, RI. Yeah, so if I make it general, it should be of the CJ, RJ. Correct? Okay, but can you tell me whether I and J can be the same? That is, can I have CI squared in B2? Why cannot I have, why can't I have C1 squared times some R, for example, in a second order circuit? So think of it in this manner. Let's say I have a second order circuit, means I have two capacitors, right? That much I know, right? So if I have a two capacitor, and let's say this, for the sake of argument, I say that I have a term in B2 which is C2 squared something, right? So let's, for the sake of argument, I say in B2 I have C2 squared some times some R, I don't know, some R1, R2 squared something, right? Times S squared. And I know that in the denominator I have B1S, which means denominator will also have some term of C1 and some term of C2. Correct? So I will have some C1 times some Rx and plus C2 times some Ry times S. Correct? So this will be my denominator, right? So this will be 1 by something. I am not writing the numerator, so I have something in the numerator. So now assume that I have set C1 to 0, right? So say C1 is equal to 0. So what is the denominator equation now? 1 plus C2 times some Ry S plus C2 square R12 square S square. Second order equation, right? But in a circuit where I had two capacitors, I removed one capacitor. Should it be second order or should it be first order? It has to be first order, right? So which essentially means that this equation should reduce, or rather this equation should not be possible if I have C2 squared. It must have C1, C2 both, right? It cannot have C2 squared. Similarly, if you generalize, if you have n capacitors, you will have C1, C2, C2, C3, C3, C4, and so on, but you will never have Cn squared or C1 squared or C2 squared. Because if you have that, which means that you can set every other capacitor to 0, but that particular capacitor which has a C squared term, and you will end up having a second order denominator for a first order circuit. So that's not possible, right? So because that is not possible, the C2 squared is not possible. This is very important because this will help us reduce the circuit, reduce the algebra quite a lot. Okay, fine. So we understand this. Similarly, similar argument holds for A1S and A2S squared also. You agree? Okay. So let's refine. So H of S is, here I have H of 0, that is the transfer constant while setting all the capacitors to 0, plus some A1S plus A2S squared by 1 plus, in the now in the denominator, the first term, which is A1S, I understand it will be having some C1 times some R plus some C2 times some R times S plus B2, where B2 will be of the form of C1, C2 times some, I don't know, RMRN times S squared. What is RMRN? We have to evaluate. But I know that it will be of the form of C1, C2. That I don't have to evaluate. That I know for sure. With me till now? Okay. Similarly, here I know that C1 and C2 will be there. And there will be C1 times some R and C2 times some R. What is that Rx and what is that Ry? We need to know. But I have solved part of the problem because I know that it will be only C1 times something, C2 times something. The next thing is to then massage my circuit in such a way that I only get this denominator, in the denominator, I only get a first order expression and I do not get any second order expression or higher order, in this case, second order, right? So can you tell me what should I do to my circuit to ensure that I get only a first order circuit, while the idea is to still get the denominator expressions partly or fully as far as the first order terms are concerned. Pardon?
Either C1 or C2.
Yeah, so I can basically either set C1 or C2 to 0, then the second order term goes off. In the denominator, I am only getting the first order term. Fine? Right? That's what this equation is telling us, right? So we are basically following the math and doing an appropriate changes in the circuit to get the coefficients. Okay. Okay, fine. So let's do that. So to get, so if let's say C2 is equal to 0, right? So we started off with the circuit that we had, which was this. So R1, 2, C1, C2. So if C2 is equal to 0, what does the denominator term look like? This becomes 1 something. Here I have something. And in the denominator, I get 1 plus C1 times some R equivalent, that is Rx, times S, and nothing else. Correct? How does the circuit change? I get this, and here I have open. Correct? Now, if your transfer function has this form, and you know that your circuit is like this, do I know what this entire term is? That is a time constant. Correct? So time constant associated with that memory element, which is capacitor in this case, this C1. So what is the time constant associated with the C1? R1 C1, right? So this, I know that this Rx will naturally become R1. Okay. So the formal way to write this, if I follow the nomenclature of Professor Hajimiri, the formal way to write this is, it's the time constant. This is the time constant of the, in this case, it's 1, but I'll generalize and I'll say ith element, ith capacitor, when all other capacitors are set to 0. Right? In English, that's what it means. Correct? In symbolic terms, we will represent this as tau, which is for time constant, I, which means the memory, the element, the index of the capacitor for which I'm evaluating the time constant. And in the superscript, I will write 0 because all other capacitors are set to 0. Correct? Okay. So, and obviously, I'll have to evaluate this for all elements. If I have 1 capacitor, I do it for 1. If I have 2 capacitors, I'll have 2 time constants. If I have 3 capacitors, I'll have 3 time constants, and so on. And once I have that, I'm going to add all of them up. And that will give me the B1 term. Make sense? So let's do that for our toy circuit. So I know that time constant tau 1 superscript 0 is R1 C1. If I have to say, I have to do the same thing for C2, then it will be tau 2, because I am talking about the second capacitor. Superscript will be, no, superscript, notation. Notation is important, you'll see. 0, okay, 0. So which means the circuit is reduced to what? Circuit is reduced to this is open. correct? So now tau 2 superscript 0 is R1 plus R2 C2, right? Is there a tau 3? Yes.
Are we doing kind of superposition, like taking every element on that?
Yeah, so it looks like a superposition, right? We are doing, we are evaluating different things and adding them together. But this is strictly not superposition, right? Because it is not superposition. But superposition means that you are not changing the stuff inside the box. You are only giving signals one at a time, right? So this is not superposition because it even though the framework might look like I am doing in parts analysis, but this is not superposition, right?
So, sir, zero here, what information is giving?
So this superscript 0 means that other than the capacitor which is written in the subscript, everything else is 0. Right? And it's more, if it will probably become more evident if I have multiple capacitors. Let's say I have this, I have this, I don't know, I have this. Let's say I call this C1, C2, C3. In this case, let's say I say tau 3 superscript 0 will mean what? I am talking about the third element, third capacitor, which we are talking about C3, and while C1, C2 are 0, right? So which means that circuit should reduce to right. Then I'm going to evaluate the time constant associated with C3, whatever it is. It will be my tau 3 superscript 0, right? So by the way, the stuff that I assumed you know, but I have not make it told it explicitly, is when you are evaluating time constant, what should you do to the source? Short, right? Or in this case, basically, you have to desensitize the source. If it's a voltage source, setting voltage source to 0 means shorting it. If it's a current source, setting current source to 0 means opening it. If it's a control source, it is remain as is, right? Because control source is not really a independent source, right? It's a dependent source. Okay, fine. Okay, so far so good. So what about the numerator? How can I get something about the numerator before I move on to the other terms of the denominator? I want to evaluate A1 next. Okay, so I have evaluated B1. I want to evaluate A1. So let me again write out what we have till now. H of S is transfer constant. H of 0 means the transfer constant when all the capacitors are open circuited. In the denominator, I have 1 plus summation of the time constant for the ith element where all the other elements, all the other capacitors are 0 and summed over 1 to n. In this case, 1 to 2 because we had 2 elements. And I have some term of summation of Ci, Cj times something, I don't know, maybe Rm, Rn. I'll just give some alpha beta term. Let's say I call this beta ij. Right? What is beta ij? We'll come to that when we come to second order. Correct. Thank you. And here there will be something on I and something on j, some limits. We'll come to that when we come to the second order term. But in the numerator, I am going to have, again, here I am going to have some second order term. This is squared times. Similarly, I'm going to have something here. But I'm now interested in whatever is here. Okay, I'm interested in A1S. So by the same argument that we have given till now, I can say that A1S will also be summation of, let me break it down, then I will write the summation. It will be basically C1 times some R. I don't know what this R is, maybe some Rm times, obviously S is there, times, plus C2 times some Rn, right? It will have this format, right? Whatever is Rm, whatever is Rn, I don't know, but it will be of this format, right? Make sense? And if I use the same argument as I used while evaluating B1, I'll know that each of these will be some time constant, but it will not be time constant only, because right now this is not associated with the pole, right? This is in the numerator. So it will be time constant times some extra factor. I need to basically find out that extra factor. Correct. So I can basically write this as, each of these terms, I can write this as tau10 times some extra factor. Let me write it as H10, or let me not write 0 for the time being, right? So let me just write it as alpha 1, and this is time constant with respect to the second element when this is 0, and let me write it as alpha 2. The job is now to find out alpha 1 and alpha 2, right? If I know alpha 1 and alpha 2, then my job is done, right? Agree so far? Okay, fine. So now, what can we do to find out alpha 1 and alpha 2? Now note that the goal again is to not overcomplicate the circuit. I always want a first order, maximum first order circuit. 0th order is even better, but maximum first order circuit. Okay, so can you give me a idea as to how to go about isolating the A1 term, given that I understand whatever is there in the till here I know, right? I do not have to isolate this if necessary, right? It can be there, may not be there, not a problem, because I already have evaluated that part. Things that I have not evaluated are this and this. So these, and if there are higher order terms, has to be taken out of any analysis, right? So what can I do to take all of these out of the analysis while still getting A1? Right. So if so let me take step by step. If I make all the capacitors to be 0, then A1S term will also vanish. Correct? Now, if I set all but one capacitor to 0, right, then there is a chance to evaluate, because in the denominator I know what there is. It will still be a first order circuit, right? I can still evaluate, but I probably will have to still write a set of equations, right? But I don't want to write too many equations. So another way of going about doing it is, if you recall whatever we said in the beginning, there are two ways of reducing the order of the circuit. One is making capacitors to be 0, or making it to be infinity. So till now only we have used setting capacitor to 0. We have not used the other handle, right? So what if I have to use the other handle, then what if I set one of the capacitors to infinite? I have two in this case. Let's say I set C1 to infinity. Right? If I set C1 to infinity, now can you comment what is going to happen? What is going to happen to H of S? So by the way, only setting C1 to infinity is not sufficient, because I would also like to get these things to go to 0. If I set 1 to infinity, tends to infinity, if not infinity, very large, then I am not able to get rid of the S squared terms in the denominator, right? So I can set one of the capacitors to infinity, but if I have to get rid of the other higher order terms in the denominator, what do I need to do? Set all the other capacitor values to 0, right? So one capacitor to infinity, all the others to 0, right? So let's say I set, then I can choose, let's say we set C1 tends to infinity, not infinity, tends to infinity, and C2 is equal to 0, right? So if, yes.
Second order term, like, won't the impact be neutralized by?
That's why I said tends to infinity. And the other is exact 0. right? So it will not be neutralized. Okay, so if this is the case, then what will, so all I need to then figure out what is the dominant term in the numerator and what is the dominant term in the denominator, correct? Because if something goes to infinity and the others are finite, I can neglect the finite with respect to infinite, right? So obviously in the numerator, I'll have h superscript 0 plus a1s. A1 has one term which contains c1, right? So that will dominate. The other terms will not dominate, correct? So which means that in the numerator, I'm going to have tau 1. Yeah, okay. So let me write it in terms of capacitors. That will make more sense. So let's say I write it as C1s times some R, right? That will be some Rm, I am saying, right? So some Rm, that will dominate. In the numerator, will I have the s squared term? Will it be present? No, right? Because I mean all other C2, if it's a generalized circuit, I can say C3 to all of Cn are set to 0, right? So all other terms corresponding to s square or higher order terms will also go to 0. So in the numerator, I only have Rm C1s. In the denominator, what do I have? I have 1 plus 1 anyway goes off because I'll have this another infinite term which will be dominant. So in the denominator, I am going to have s times some, again, I mean, basically the R equivalent for with respect to the first capacitor. And so I can then basically write it as gamma tau 1, right? Tau 1 and under, and what should I write in the numerator now? So that's the important, sorry. I think I made a mistake here. You were saying something? You mean in the numerator? No, it will be there, but this term will dominate, right? So I'll have h superscript 0 will be there, but I am setting C1 to infinity, right? So this is C1 to infinity. So if that is there, then I can basically neglect that h superscript. Okay. In the denominator, I am going to have, if I write it in the form of C1 itself, so this was C1 times that R equivalent, which formed the time constant, right? So this was whatever it was, Rx we chopped, right? So let's say I call this Rx, right? So this SS goes off, right? So in the numerator, I can basically say that, yeah, if I say the numerator is, okay, but in the denominator, this is tau 1 superscript 0 by definition. In the numerator, I will write it in the form of tau 1 superscript 0. So I am going to get some tau 1 superscript 0 times something, right? So basically, this is Rm over Rx. Correct? And how, so now what is this Rm over Rx? There is a, we'll denote a, because ultimately I have cooked up this terminologies Rm and Rx and all, right? They have to be properly defined as to what do they mean, right? So what does it mean? So this is basically this Rm, this cancels off and I get Rm over Rx, right? But I understand the algebra tells me this Rm over Rs, but what does this Rm over Rx mean? This means that this is the transfer constant under the condition that C1 has gone to infinity and all other capacitors have gone to 0, right? So I can basically denote this as this is equal to transfer constant when a transfer constant, by the way, I should mention if explicitly in this case between Vi and V naught, when C1 has gone, it's tending to infinity, and all other CIs are equal to 0. CI where I not equal to 1 are exactly 0, right? So there is a nomenclature for that. Just I do not want to write this entire thing every time. So the nomenclature is, it's a transfer constant, which means it should be H, right? The index should be of the term which okay, hold on. Yeah, so index should be of that corresponding to the capacitor which I'm evaluating for. But in the superscript, I cannot have 0 now, right? In the superscript, if I said 0, I essentially mean that all the other everything is 0, right? So in the superscript, that's why I'm going to put that value of the index for which the capacitor has gone to infinite, right? So this can be a bit confusing, but I'll clarify. So for now, let's assume that this is H1, 1. Okay. So forget about this subscript for the time being. Okay. So forget about the subscript for the time being. I have made a mistake in this definition. I will rephrase again. So forget about the subscript for the time being. So anything in the superscript, it becomes non-zero, right? So if superscript is 0, then all C's are all C's are 0, right? Because H0 was when all C's are 0, right? But if superscript is non-zero, correct? And let's say in this case, whatever index I have index of 1, right? Then the C's corresponding to the index goes to infinity, and all other capacitors also go to 0, right? And all other C's where all other Cj where j not equal to I, let's say in this index I, goes to 0, right? It's a very big statement, but should make intuitive sense. Okay. This subscript, the way Professor Hajimiri has treated it is, I'll just verify it once before I make the next statement. So this subscript is 1 in this case. This subscript does not mean index. Okay, this subscript means this 1 because I am trying to figure out the transfer constant corresponding to S term. Okay, so when I'll be trying to figure out the transfer constant corresponding to S squared terms, this 1 will become 2. Okay, so similarly, so this subscript is basically the corresponding to the to basically B1 or A1 in this case. Okay, fine. So if this is, if we are comfortable with this, now let's go back to the circuit. Yes.
Now I0, the 0 subscript here,
Yes, yes. For H, it means, yeah, correct. Yes. Okay, so this is C1, this is C2, R1, this is R2. So now what we have again, I know what the denominator is, 1 plus R1 C1 plus R1 plus R2 C2 s plus something times s square. In the numerator, I have 1 plus this one I want to evaluate, and this one we'll see later. So in order to evaluate this, I understand this is of this form of h11 tau 10 plus h12 tau 20, right? So what is h11 in this particular circuit? So by definition, h11 means C1 is infinite and C2 is 0, right? So this means that C1 tends to infinity and C2 is equal to 0, which means what is your circuit reducing to? This is shorted, this is open, and this is your V0. So what is H11? 0, right? So all this song and dance to get only 0, right? Okay. So what about now? I'm pretty sure you don't need to evaluate this explicitly. What will this be? Again, this by definition is C2 tends to infinity and C1 is equal to 0. So what will this be? Zero, right? So this entire term goes to 0 in this particular case, right? Now, if okay, so you mean tau 10, that one? Okay, so that is same as when we use this transfer function. Sorry, when I am doing time constant here, right? Where was it? So this guy. So what does this mean? This means that once I'm trying to find out B1, what did we do? We basically said that all capacitors other than the index that I'm interested in is set to 0. Why am I doing that? By the way, the stuff that I did not explicitly mention, the reason this works is because I know that the poles of your transfer function are set by the time constant only, right? The corollary to that is that the poles are not dependent upon where you are applying the input or where you are taking the output from. I'll come back to your question. I have not answered that, but I'm basically addressing the entire class that the reason I have been able to do whatever we have been able to do is because while evaluating the denominator, I did not need to bother about where I have taken the input or I am taking the output. We all agree with that? Because ultimately, if you go back to the way these circuits were formed a long time back, so how do you go about doing it? You write a differential equation, right? A forced response you set to 0. You get some differential equation, and then you took a Laplace of that. And you get some s square, s cube, and blah, 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 everything. And that essentially becomes the auxiliary equation. The roots of that are basically the poles. If you recall, I mean, circuit theory, when it was taught to us first time, this is how it was developed, right? So it does not, in order to evaluate the roots, the first thing you have to do is to set the forced response to 0, which essentially means that no input and no output, right? It's a natural response of the system. Okay, so the poles do not depend upon where you are applying the input, where you are applying the output, where you're taking the output from, but the zeros do. Numerators are actually needed, the inputs and outputs are needed to evaluate the numerator. So that is why the strategy was to use this fact that in order to find out the denominator, I don't need inputs or outputs. I can desensitize the inputs. And only if, after doing that, if I can reduce the circuit to a first order system, then I have to only look into the time constant of that reduced first order system to get to the denominator terms, right? But in order to get to the numerator, I cannot do that because the numerator depends on input and output. Where I have applied the input, where I have taken the output. So I need a different strategy. So once I have gotten the denominator, the next strategy becomes how can I apply, how can I change the values of the capacitors in order to get to those proportionally constants in the numerator. Okay. So now coming back to your question, what is so this tau I0 has been introduced to get the terms of the denominator, time constants, right? So, and because if you have multiple capacitors, in principle, I can say that for each capacitor, when all the other capacitors are 0, I have one time constant. If I have n capacitors, I can have n time constants. I want to evaluate each time constant at a time, right? Associated with the capacitor. So that's why when I set ith capacitor time constant, so I have to set all the other capacitors to 0. That's what this notation means, right? I am evaluating the time constant associated with the ith capacitor while setting all other capacitors to 0, right? So, but this was in the denominator case. But in the numerator also, this will appear because you can follow the same argument, right? Having everything to 0 and all. But we understand that the numerator will have this term plus multiplied by some another term, because where I am applying the input or where I am taking the output, depending on that, that gain can change, for example. Yes.
When we are taking T1 to the infinity and
Right.
rest of them to 0.
Right.
The notation we are using for transfer function is changing also. Like
yes, it is changing, and that change is captured by this transfer constant term h. That is appended with the time constant. This h1 times the time constant, right? So if you see, I thank you for pointing it out because I did not close the discussion. So this becomes a time constant, right? So this is h11, correct? So effectively, if you see in the numerator, I am having what? In the numerator, in the denominator. So in the numerator, I am having h11, this times s, and then blah, 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 blah. Here I have, in the denominator, I have only having this. Sorry, 0. Right? Yeah, good catch, because I did not complete the thought here. So I jumped one step. Yes.
You are writing one is tau and V. Like RM is there and
But they also have C1, right? So if you think about it, so what am I looking for? I am essentially in the denominator, I have. So okay, so let me maybe clarify it a bit more. So if let's look at this term only, right? So I had in the denominator, I had 10s, and in the numerator, I had Rm over Rx times tau 10, right? So I'm basically rewriting this part. I understand the confusion that is happening. The confusion is happening because I have written it in this format, right?
from where this RM by Rx is.
So see, if you go from this format to tau format, then you get that Rm by Rx extra term, right?
The tau itself contains some
Correct. So, okay, what the reason I am doing this, okay, so let me break it down. So I can write this Rm times C1 to be Rm by Rx times Rx times C1, right? So this is basically tau 1, 0. So that's what I'm writing it as, right? So this becomes tau 1 superscript 0, right? And I can do it for each of those terms individually. Make sense? But yeah, thank you for stopping, because otherwise this would have been a source of confusion later on. Fine. So the reason I was harping on this position of the zeros, I mean, the example that I took might seem that, I mean, why do I do all these things if ultimately everything comes to 0? All I need to do is to say that I will not take the output from where I was taking. I will take the output from, let's say, here. Let's say this is my V0.
It will be S2, that will be 2, right? Second, A2 test.
No, this is not the index. So that is basically the which order term I am evaluating. I am evaluating A1. So that's why it is 1. When I will evaluate A2, that will change to H2. Yes. The C corresponding to, if superscript is 0, this definition is with respect to superscript. Index I, right? So basically this 1 is I. Right? So, okay. So I'll just write it as I, if that helps. Correct? But yeah, I mean, could have been a confusion. Yes. Fine. So let's say I now, I mean, circuit doesn't change. Only I am tapping it from the output point change. Do you think B1 is going to change? No. Anything in the denominator is not going to change. But in the numerator, things can change. Correct? So in this case, what is H superscript 0? All capacitors are open. I'm taking the transfer constant across V0 while applying Vi. So which is equal to then? So the circuit reduces to what? This is my V0. One. Right? Okay. So it was 1 earlier also, it is 1 now also. There's no change. I mean, no change, not because it's by, I mean, it will always be no change, but just the way it has been, a circuit has been constructed. But there will be a change in H11, right? So H11 will be what? While we're doing H11, what should I do? So this will go to infinity and the other guy will go to 0. So this is still 0. What about H12? So what will happen to C1? C1 will be open because C1 goes to 0. And this is going to get shorted. This is R2 and this is V0. So this becomes R2 by R1 plus R2. Correct? So depending upon where you evaluate, where you want to take the output, we are almost out of time, only in first order. Okay, so depending upon where we are taking, trying to take the output, your A1 can change. Now here I would like to point out the fact that already you should, even though notations might seem clumsy, it might take getting used to for some time, but you should appreciate right away that if you had to write out the KVL and KCL, just because your output point changed, you would have had to go a substantial amount of rework to figure out what the V0 would have been. But in this case, no, not required. Because if you have evaluated these terms individually, each term can has its own equivalent circuit. If I have to put it that way, right? and that the equivalent circuit for each corresponding term is either a first order, where you have to evaluate a time constant, or 0th order, where there are no capacitors at all, right? Either capacitor has been set to infinity or set or to 0, right? Make sense? Make sense? Okay. Okay, so I'll not start the second order one today because it will take another half an hour. So what I'll do is try to motivate as to why. So where are we now? So what have we found out? So we have found out that I can find out H superscript 0 easily. I can find out the denominator first order terms easily. And so this is tau I0 S. In the numerator also, I can find out and then I will have second order terms, which we'll leave it for next class, right? But the key thing to note here is that in many applications, you will see that we probably don't even require the higher order terms to evaluate the 0th order dynamic or the first order dynamics of the circuit. The reason is, let's say you have a first order circuit. If you have a first order circuit like this, and forget about the numerator for the time being. Let's say you have only a first order circuit which has this H0 by 1 plus B1 S, right? Can you comment on the fact that can B1 be complex? How? What is B1 made up of? R and C's, right? Can B1 be complex? B1 cannot be complex. Which means that the poles cannot be complex. It's a first order circuit. The poles cannot be complex, right? So in a first, so that is something to keep in mind. But that does not mean that the pole of this system is complex, by the way, right? All I'm saying is that if it is a first order circuit, then the poles cannot be complex. But if I know the poles of a first order circuit, what all things can I easily figure out? Can I figure out bandwidth easily? 3 dB bandwidth? I can figure out easily, right? What is the 3 dB bandwidth in this case? So how do you figure out 3 dB bandwidth in general? So you set this to j omega s equal to, right? And take the magnitude of this and set to 1 over root 2. And you evaluate the value of omega for which this happens. And wherever this happens is your 3 dB bandwidth. And do you know the final thing? What will come out if I do this exercise? So this would be h 1 by 2, by the way. So what will it be? What will be that value of s for which this is going to happen? Yeah, so this is after you do this and you again go back from omega to s, so you are going to get your pole location to be P1, since the first order only one pole, P1 to be is equal to 1 by B1. Actually, it's negative 1 by B1 because it will be a left-hand side pole, but if I'm interested in only the magnitude part, assuming it's a stable system, it should be okay. Okay, and I know B1, which is basically a time constant, or if I have reduced the circuit to a bigger circuit into a smaller part, I know it's summation of some time constants and so on, right? So quickly you can figure out what is the approximate expected bandwidth. There will be error, obviously, because you have neglected other higher order terms, but you have an idea of what the bandwidth will be to start off. So this is extremely important when you are designing. When you are designing, you don't have an idea of what to start with, right? When you are doing analysis, a circuit is given to you and you go step by step by step by step, you get something. But when you are designing, the answer is given to you. I am asking you to form the question, right? Which means the expected output is given to you. I am asking you to form the circuit. That's what design is. You have to think in the different direction. So you need a starting point. So how do you know a starting point? If I tell you design an RC ladder, I mean, effectively the ladder that I told you right now, this is the architecture I tell you. And so the design an RC ladder for a bandwidth of 1 megahertz. So you have to start somewhere. with the component values. So if you know that, I know that the 0th order, even the first order equivalent will be this, then I know that this gamma I 0, a summation of this, which is equal to R1 C1 plus R1 plus R2 C2, should be is equal to P1, right? Mod of P1, or should be equal to 1 over B1. So that can be your initial starting point without really designing anything. So that's why this framework is useful. Another reason it is useful is because if you have to quickly look at a circuit and tell me, without really simulating or analyzing much, I want to know whether I have these two RC ladders. Tell me which the step response of which one will be faster. That is, which one will settle faster. So I know that the step response is also related to bandwidth, right? Bandwidth essentially means that if you have higher bandwidth, it will settle faster. You will reach your destination quicker. That's all it means, right? So if a ladder has a higher bandwidth, it's expected that it will settle quicker, right? So I can basically get an intuition behind which circuit will be faster by how much also with respect to another circuit to a 0th order level, that whether one will be faster or slower, having higher bandwidth, lower bandwidth, and so on and so forth, right? In the next semester, most of you are going to take a course on VLSI system design, where you will see that how a piece of wire is modeled. It's basically modeled as lumps of RNCs and RNCs and RNCs. And they are also, you do not really have, you do not sit and calculate what is the effective, what will be the exact delay from point A to point B, given that you have so many RNCs. There also, you reduce it to some first order circuit. And you will see that the formula that is used is basically this. That is the delay, right? So, basically you get 2 lectures of next semester done by only knowing this. Okay. Okay, fine. So, any questions before we stop? No questions? Okay, fine. We'll stop here. What I'll do, I'll post this and I'll also give you the link to this paper. You can download it, read through it. Extremely well-written paper. In my opinion, there are some papers or tutorial papers which every circuit designer should read. This is one of them. Okay, so read it. Okay, thank you. Yes.
Is this method of finding like numerator coefficient is the transfer constant like an intuition for finding the half of the circuit?
Yes, yes. So we are going to see, you can also find out how many zeros are there without really evaluating locations of the zeros, everything, all of them, everything you'll be able to figure out.